Okay, now let's talk about the sharpening process. Again, in kernel-based neighborhood processing, we only talk about two objective or two main filtering mechanism, which is a smoothing filtering operation as well as a sharpening filtering operation. Okay, in sharpening filtering operation, in contrast with smoothing, the main objective of sharpening is to highlight the fine detail. Okay, means that that is actually is in contrast with the smoothing, because smoothing we want to remove the fine detail and then we just remain the gross detail. But for sharpening, we want to highlight the fine detail or enhance the detail that have been blurred. Okay, so okay, in sharpening process, there are two main filter involved in order for you to obtain a sharpening filtering process. There's a two main filter you need to compute with your input image for you to obtain the sharpened image. One is what we know as a special differential filter, or in some books they call it a high pass filter. Another one is all pass filter. So in order for you to get a clear pictures about how to operate a sharpening filtering operations, now let's take a look at this whiteboard. Okay, we already discussed about how the smoothing filtering operations before. So it's a direct two-dimensional convolutional operations, and then it depends on which one you want to use, which kernel you want to use. Is it you want to use average filter or Gaussian filter? And then once you select one of it, you just convolve with your input image. Then you can perform the output image that you obtain is actually of the output after you applying the smoothing filtering process. Now let's take a look at this sharpening filtering operation. Okay, for a sharpening process, actually is quite a complicated as compared to smoothing. Okay, smoothing you just directly apply the two-dimensional convolution between your input image and either your filter, average filter or Gaussian filter. But for sharpening filtering operation, okay, it involves two blocks there. Okay, it's not just one block like this one. It involves two blocks. One is this one, WAP. Okay, this is represent all pass filter. Okay, if you see your slide there, this one is all pass filter, and another one is high pass filter. So this one is all pass filter, so that's why I call it WAP, all pass. So this one is a all pass filter, and this one is high pass filter, and also known as a special. Also, okay, that filter is also known as special differential filter. Okay, all pass filter or special differential filter, this one. Okay, and then to get the sharpening, okay, actually the sharpening filter operation is all of this one. Okay, if you sum all, okay, everything here, if you compute, then you produce G over here. That is a sharpening filtering operation. Okay, now let's discuss about this one. This is also known as high pass filter or special differential filter. Once you apply this, okay, when you do a convolution between the input image and this filter, the output of this convolutional operation, you will obtain this one, which is represented by this nabla square fxy. Okay, this one is just a symbol. Okay, you don't worry about it. Just represent any this one is represent the output after you do a convolution between the input image and the high pass filter. Okay, once you apply this one, okay, in this one, okay, this high pass filter, as you can refer to our slide, you can have 4 different type of kernels there you can choose. Okay, it is like your smoothing, it's like your smoothing filter operation. You can choose 2 filter. It can be average filter or Gaussian filter, but this one you can use any either A, B, C or D. You just put it here and then you convolve with this input image, then you get this nabla square fxy, which is the output after you applying the high pass filter and input image over here. Okay, this kernel is known as Laplacian filter. Okay, so this is known as a Laplacian filter. So doesn't matter A, B, C and D, everything here is known as a Laplacian filter. You can choose one of it to be put here, convolve with this one. Okay, and then this line over here, okay, you it consists of filter known as all pass filter. Okay, the name of the filter represent what is the purpose of the filter. Okay, all pass filter means that this filter will pass all the signal from the input into the output. So that's why you can see that I write here, if this is fxy, when you apply the all pass filter, then the output here should also fxy. Okay, because the all pass filter is actually like, you know, it's actually like there's no blocks there. It's like, look like if you delete this one, okay, if you just delete this one, you just cancel this one, and just you continue this line to this line over here, then that is the purpose of all pass filter. You can see that all pass filter seems to be do nothing there, meaning that it will pass anything from the input to the output. Okay, so that is the all pass filter is all about. So just to discuss a little bit details there, okay, because in the slide there is mentioned about when you talk about the all pass filter, this is the kernels. So I just draw the kernels there. This is the all pass filter look like. Okay, then I try to draw the kernel in this form, impulse response form. Okay, you can see at the center you get one impulse once there, then the rest you get 0 0 0. Okay, only the point at 0 0 you get the amplitude equal to 1 for all pass filter. Now let's try to relate with this two-dimensional all pass filter with the one-dimensional concept. Okay, if you talk about the one-dimensional concept, if you remember, if you talk about this thing, okay, this thing in one-dimensional, it's look like this one. Okay, this is actually is all pass filter for one-dimensional signal. So if you have yxn, which is equal to convolutional process between your xn and hn, if your hn equal to 1, which is this one, then your yn is equal to xn, because imagine, okay, let's say this is your okay, this is your xn. Okay, this is your xn. Assume this is your xn. Okay, if you convolve this one with this one, again you flip the hn. Okay, because your hn is only have a value at the 0 there. Okay, this is 0. If you flip, nothing happens. Okay, meaning that the same hn you get, because you only have value at the origin there, 0. Okay, that's why if you flip, you still get hn. Then after you flip there, you slide into this window for the convolutional operation, and then you slide into x axis value or n there, and then at the end, after you apply the sum of product, you still get the same xn there. Okay, this one become 2, this one become 1, this one become 1. So in other words, if this hn is look like this, and then if you convolve with xn, then your yn is equal to xn, because nothing happens there. Or in other words, we also call this one as all pass filter, because it pass everything from the input to the output side. So this terminology same goes to two-dimensional signals, because in two-dimensional signals, if you talk about this is the all pass filter for one-dimensional. Now for all pass filter for two-dimensional is look like this. Okay, the difference only this one in two-dimensional signals, this one is in one-dimensional signal. So in other words, if this is convolved with fxy, then at the output side here you still get your fxy. So that's why I write here fxy as well, because it seems like this operation or this block seem to be non-exist there. Okay, even if you extend this arrow and then you skip or you remove this filter, then it's look like that things, meaning that nothing's there. Okay, just this is okay. You can also replace this thing with, if you remember in point processing we talk about identity transformation function. Okay, if you put it there, then you also do the same things, meaning that all input will become all the output pixel is equal to all the input pixels there. Okay, it's do nothing's there. But why we still put this one as all pass filter? Because of the operations there. Because in other words, even this is all pass filter, okay, actually you can skip this one. You can simplify the block diagram by delete this one, because now this one is all pass filter. You just delete this one, and then you just extend this line like this. Okay, so at the end, because this one is similar to this one, so even without this one all pass filter, okay, you can cancel this one, then the input and the output is similar. Okay, so once you now how to get the G there? So to get the G, okay, there's a several way to get the G. Okay, this is the equations there, okay, which is I copy from the slide as well. Okay, the nabla square fxy here is this one, where this is the output after you convolve between this one and your input image there. So it's depend on which kernel you use. If the kernel you use kernel A or B, okay, to apply this one, then to get the G you must this one plus this one. Okay, but if you are using this kernel C and D to obtain this nabla square fxy, then to get G, your F must minus this one, this nabla square fxy. So that's why I put here it can be plus or minus. So this plus or minus is depend on which kernel that you use to obtain this nabla square fxy over here. Okay, so that is the operation, meaning that sharpening operation you got many version. You can use this one, type 1, type 2, type 3 or type 4. You can use A, B, C or D, and then it's depend on which one you will use. If you use A or B, then this operation plus this one you will get G. But if you use C or D over here, then you must this one minus the output of this one in order for you to obtain the sharpened image, which is your GXY. Okay, so that's explain everything in this slide. Okay, this one as well as this one.